Problem 15. What is the remainder of 2 power of 2020 when it is divided by 5? Okay, so we have the number. Okay, we have the hint. We need to find the pattern. Okay, so let's set up, okay, a table. So we have 2. So we divide by 5. So what is the remainder? Okay, divide by 5. Remainder. Here, so 2 divided by 5 is 2. Okay, 2 square, 4. The remainder is 4. 2 cube, 8. So the remainder should be 3, and the 2 fourths power, 16. So remainder is 1, and the 2 fifths power, 32. So remainder is 2 again, right? 2 sixths power, 64. So it's a 4. Okay, so far we can find the pattern is every 4 number will repeat 2, 4, 3, 1, this pattern. Okay, so we have the number is 2 power of 2020, so we just use 2020 divided by 4, it's 505, and the remainder is 0. So that means it will be repeated 505 times of this pattern. So the last number would be, remainder is 1. So divide by 5. So then actually we can write like this, okay? We can 1 and module 5. So that means divided by 5, remainder is 1. Okay, so our solution is B then. Problem 16, for how many positive integers n would satisfy this inequality? So let's convert these 3 fractions to the fractions having the same denominator. Okay, so the least common multiple of 653 is 30, right? So we can convert like this. So 6 times 5, 1 times 5, less than n times 2, 15 times 2, okay, less than 1 times 10, 3 times 10. So then we will have all the fractions with the denominator 30. Okay. Okay, so then we can finally multiple of 30 of all the fractions. So 5 less than 2n, then less than 10. So divided by 5, or divided by 2 of each number, so 5 over 2 less than n, less than 5. So n has to be positive integer, right? So this is 2.5, so n has to be 3 and 4. So 2 positive integers satisfy this inequality. So the answer is B. Problem 17, if n is a positive integer, satisfy this equation. So what is n? Okay, let's look at the hint. Okay, so from the hint, we might think 1 over n minus 1 times n could equal to the question mark. Okay, 1 over n minus 1 minus 1 over n. Okay, so let's prove it. Okay, so 1 over n minus 1 minus 1 over n. So we have a common denominator, 1 times n minus n times n minus 1, n minus 1. So we subtracted the numerator, 1 minus n minus 1. So n, oh, this is n, so cancel n. Negative 1 is 1. So n minus 1, n. Okay, so we prove it. So then we use this formula to replace the equation, okay, this expression. Okay, so 1 over 1 times 2, it would be 1 over 1 minus 1 over 2, according to this formula, right? So 1 over 2 times 3 would be 1 over 2 minus 1 over 3. so forth. Okay, until the last term, we will have 1 minus n minus 1 plus, and 1 over n minus 1 and 1 over n. So this whole thing, so, okay, so that will be canceled out, these terms. And also these terms would be canceled out from the previous term. Okay, so finally we got 1 minus 1 over n equals to 19 over 20. Okay, so let's just simplify. So 1 minus 20, 1920 is equals to 1 over n. So that is 1 over 20 equals 1 over n. So n equals 20. So the solution is D. Problem 18. 3 different views of the same cube are shown. The letter on the face opposite E is. Okay, so let's first to see what are those 6 letters. Okay, so we have E, we have L, we have I, we have C, we have U, we have D. Oh, actually it's Euclid. Okay, Euclid. Okay, so then we look at these 2 cubes. So it's so from take a look at the letter E on the top. So it is 180 degree rotation. So 180 degree rotation this way. So then E becomes this. Okay, so 180 degree. So then C, U. Okay, so the L, I rotated that. And then here, this one is U. So this has to be U. This has to be C. So we rotated 180 degrees. So U is here and C, letter C is here. So then we just have to have D at the bottom face. Okay, so the letter on the face opposite E is D then. B. Okay, the answer is B is right. Problem 19. If A, B, C are distinct digits, which of the following numbers cannot be the largest possible 6-digit number written using 3 digits A, 2 digits B, and 1 digit C? So we have 6 digits number. So we need to put the largest integer in the largest place value. So this one is largest integer. That one digit and the largest digits. Okay, the other one is second largest digits. And that's the third, fourth, fifth, and sixth. Then we know the largest digit, of course, is great equal to second largest and the great equal to third. So we have these relationships. Okay, so let's look at the answer. So A, this one. Let's look at this answer. A, B, C, B. According to this relationship, so we'll have B great equal to C and great equal to B. So only when B equal to C could satisfy this inequality, and we know BC, they are distinct digits ABC, so that's impossible, okay? So that means this one, actually, we won't have as the largest possible 6-digit number as AAABCB. So let's look at the other answers. So for example, AAABBC, so we can let A equals to 3, B equals to 2, and C equals to 1. So AAABBC would be 3, 3, 3, 2, 2, 1, which is the largest 6-digit number created by these 3 digits. Okay, so also this one. So we can have C equal to 3, A equals to 2, and okay, so this one, A equals 2 and B equals to 1. So then we have 3, 2, 2, 2, 1. So which is the largest possible 6 digits? Okay, so BBAAC, we can let B equals to 3. Let A equals to 2, C equals to 1. So our number is 3, 3, 2, 2, 2, 1. So this is also the largest 6 digits numbers. For the last one, we can let A equals to 3, C equals 2, and the B equals to 1. So we have 3, 3, 3, 2, 1, 1. So that is also a largest 6 digits number formed by AAACBB when A equals 3, C equals 2, B equals 1. So only AAABCB that could not be the largest possible 6 digit number. So the answer is D. Problem 20. The integers from 1 to n inclusive are equally spaced in order around a circle. The diameter through the position of the integer 7 also goes through the position of 23 as shown. What is the value of the n? Okay, so we have this circle, we have the integer 1 to n, and placed on the circle in order. So we have a diameter. The line segment connects 7 and 23, so then the center of the circle has to be on this line. So this diameter, the line connects 7 and 23, basically splits this circle into 2 semicircles. So if we can figure out how many numbers on this semicircle, right? So these numbers would be like 8, right? 9, 10, until 21, 22, and 23, right? So how many numbers on the semicircle? Then we know how many numbers on the entire circle. Okay, so let's review how to count how many numbers of a consecutive integer list. Okay, so we have, for example, let's have a consecutive integer number list like 3, 4, 5, 6, 7, 8. So if we count how many numbers, if 3 and 8 is inclusive, okay, so we have is 8 minus 3, and we need to plus 1, right? So the formula actually is the number equals, okay, this is equals 6, right? 1, 2, 3, 4, 5, 6 total inclusive, okay? So it's the last number minus first number and plus 1, okay? So then we have 6. And if 3 and 8 not inclusive, so then we have 8 minus 3 minus 1. Actually, that is a 4, right? Not inclusive, only 4, 5, 6, 7, only these 4 numbers, right? Between 3 and 8, not included 3 and 8. So that's the 4 numbers, okay? So the formula equals to last number minus first number and minus 1, okay? So let's look at here, right? We have 7 to 23, okay? So let's count how many numbers between 7 to 23 and not inclusive of 7 and 23, okay? So then we have to use this formula, okay? So how many numbers? Actually, it is 23, subtract 7, and subtract 1. So that equals 15. Okay, so we have 15 numbers between 7 and 23, not included 7 and 23. So because this is a semicircle, so this should be symmetry to this semicircle, right? So then we have 15 integers on this semicircle. They should be equal amount of integers, right? So then we have 15 here and the 15 number here, then add 7 and 23, two numbers. So total we have 15 plus 2, 32. Okay, which is B.